Dear students, I welcome you all to another video session on design of asynchronous sequential circuit. Design of asynchronous sequential circuit. This topic is very important topic of your fourth unit. Okay, and this is a topic which is frequently asked in your university exams. So we have seen a design of synchronous sequential circuit, and in case of a synchronous sequential circuit it is quite simple because the problem is direct. But here in case of asynchronous sequential circuit, they will specify you a problem statement. Okay, so depending upon the problem statement, you will have to design or you'll have to frame the state diagram. And you have to understand the problem statement well. Only then you can frame the state diagram correctly. So once you frame the state diagram correctly, the rest of this procedure or the rest of the steps are quite simple. Okay, and I request all the students to have a pen and a paper so that you can note down the problem and you can follow the steps which I am explaining to you all so that you will have the continuity. Okay, so let me write the problem for you. The problem is design an asynchronous sequential circuit with two inputs x and y with one output z. So here is the problem statement. Whenever y is 1, input x is transferred to z. Input x is transferred to z. Whenever y is 0, the output does not change for any change in x, So dear students, you can have a look of the problem once again. Design an asynchronous sequential circuit with two inputs x and y with one output z. Okay, so whenever y is 1, this is what is your problem statement. So whenever y is 1, input x is transferred to z. Okay, so let me write this as one of the key point. So whenever your y is 1, your x, whatever is there in x, is transferred to z. Correct? What's the second key point? The key point 2 is whenever y is 0, the output does not change. That is, the output, there is no change for any change of input x. Either x can be 0 or either x can be 1. So for any change of 0 or 1, the output is not going to change for your input, for your y being 0. Okay, so these are the two conditions. Based on these two conditions, I am supposed to frame the state diagram. Okay, so let me write the inputs first. So let me write the inputs. So it is x, y, my two inputs, which is given in the problem clearly, and z is my output. Okay, so the two inputs is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so we already know that for any inputs there are two possible cases of output, right? 0, 1, 0, 1, 0, 1, and 0, 1. Now let us interpret our first statement, first key statement. What does it say? Whenever y is 1, your x is transferred to z, right? So whenever my y is 1, see the condition over here. Now the y is here 1. So whenever my statement y is 1, my x is transferred to y. Sorry, my x is transferred to the output z. So this condition holds good, right? So this is not applicable, right? Next, where do I get a y1? Here. See, my input y is 1. So whenever my input y is 1, x is transferred to z. Right, x is transferred to z in the sense my 1 has to come in the output, right? So this condition will be eliminated. So this will be in the circuit, right? Now you can see that out of 8 cases, out of 8 possible inputs, my final state table is reduced to 6. 1, 2, 3, 4, 5, 6. Therefore, let me write that. So my reduced, my state table, final state table is 0, 0, 0. These two possible cases are there, 0, 0, 1. So these two I've written for this inputs. The next is 0, 1, 0. And next is 1, 0, 0. The next possible case is 1, 0, 1. And the last possible case is for 1, 1, I have a 1. For 1, 1, I have a 1. Correct? So totally my state gets reduced to 1, 2, 3, 4, 5, 6. Okay. So let me name this as, say this is my A state, this is my B state, this is my C state, this is my D state, this is my E state, and this is my F state. Okay. Now for your better understanding, okay, so A state consists of two inputs, say 0, 0. So let me write like this. A is 0, 0, and what is its corresponding output? Its corresponding output is 0, right? So B is 0, 1, and its corresponding output is 1. C is 0, 1. You can see here C is 0, 1, and its corresponding output is 0. D is 1, 0, and its corresponding output is 0, right? And E is 1, 0, and its corresponding output is 1, correct? And final state F is 1, 1, and its corresponding output is 1. Clear? So this is our first step. So I can write this as my first step. Okay. So let's go to our second step. Okay. So our second step is, let me write this as second step. So step 2 is reduced state table. So we have to frame a reduced state table. So in the previous state table was a state table consisting of 6. Now we'll have to form a reduced state table with the next state. Okay. So I'll write the same inputs again. So we have X, Y, Z. So we got an input. I'm reproducing the same thing. For 0, 0, we had a 0. This was state A, right? So let me draw this tabular column so that you understand it better. Okay. For state B, we had the condition. For state B, we had the condition 0, 1, right? So the state B, we had the condition as 0, 0. Start. So representing, seeing the previous table, we got A 0, a state B was 0, 0, 1, right? A state C was 0, 1, 0. A state D was 1, 0, 0. I'm writing this exactly from the previous table. So E is 1, 0, 1, and our F is 1, 1, 1. Dear students, this was exactly from the previous table. Now we know that the inputs of A is 0, 0, right? So when the input A is 0, 0, its output is 0 here, right? So for A to have the race condition, so race condition is something when there is, change in the position or change in the bits, 2 bits, change in 2 bits, then you say that a race condition is prevailed in A. For example, the input A has 0, 0 over here. So if I change this A as 1 and B as 1, okay, so there is change in 2 bits, right? So this is called as race condition. So this race condition, so for 0, 0 condition of A, if it is 1, 1, because here 0 is changed to 1 and here again 0 is changed to 1. So 2 bit changes occurs, then we say that the race condition is prevailing, right? So for A, 1, 1 is the race condition, so this cannot come as a combination. So what are the combination can come for A is, I can change only a 1 bit. So I can include here a 0 and 1, and I can include a 1 and a 0. Okay. Now come to my second condition B. Second state B is 0 0 for 1. So B is input is 0 0 for an output 1. So for here again the race condition is 1 1, right? Because two positions I am changing. So for 1 1 being the race condition, this cannot happen as an input. So I can have only one bit change. So I can include a 0 1 and 1 0. So come back to C. C is input is 0 1 with the output 0. So the race condition over here can be what? It can be 1 0 because I'm changing the position 2 bits, right? So 1 0 is my race condition. So 1 0 cannot happen here. So I can change this inputs as 0 0 and 1 1, correct? Coming to D. D's input is 1 0 with an output 0. So the race condition can be 0 1, right? So 0 1 race condition will not occur. Apart from that, you can include 0 0 and 1 1. Okay. So because it is changing only one bit, that can be included in a variable. Next is E. So E has an input of 1 0 with an output 1. So the race condition of this, if I have to change 2 bits, then it is 0 1, right? Because 1 is changing to 0, 0 is changing to 1. So this is the race condition, and this race condition cannot occur in a circuit. So let me change 2 bits again. I can include here 0 0 and 1 1, correct? Then coming to F, I have 1 1 and the output being 1. Okay, so the race condition over here will be exactly 0 0 because it is changing in 2 position. So 0 0 is the race condition here, and this cannot come in a circuit. So I can include 0 1 and 1 0, correct? So these are the possible combinations. You can see that these are the possible combinations, and for these possible combinations we will check out our key condition 1 and 2. Okay, so what do our first key condition say? That the first key condition say that whenever y is 1, whenever our y is 1, what happens? Our input gets transferred to z, right? So here I will get a 0, correct? And my second condition, what does it says? Whenever y is 1, sorry, whenever y is 0. So whenever y is 0, what happens? Whatever may be the input x. See, whenever y is 0, whatever may be the input x, okay, what happens? There will not be change in the output. Okay, so whatever be. So I'll consider this. So whatever be the change in the output, my output will have no change. Hope you understood this, right? So come back to this. Now check out here. The first condition is whenever y is 1, what happens? Whatever is in x comes to my z, right? The next condition, whenever it is y is 0, whenever y is 0, so whatever is my input, maybe it is 0 or 1, my output remains the same, right? So my output remains the same. So my output remains the same. Now come back to here. Whenever my output y is 1, so my output y is 1, so I'll get the same. X is transferred to y here, x is transferred to z here. And whenever my output is 0, so whatever is my input x, okay, I'll get the same output. Now come back here. So whenever my output y is 1, whatever is in x comes to my z position. And when it is, whenever my y is 0, so maybe my x 1 or 0, so whatever is in my output will come back to this output. Okay. Now the next case, whenever my y is 1, what is in x comes to my z, and when my y is 0, irrespective of 1 or 0, the same output will be produced here, correct? The last case, whenever my input is y is 1, x comes to z, and whenever y is 0, irrespective of my x, my output comes here, right? So whenever my y is 1, so whatever is in x, okay, so whatever is in x, so what is in my x is 0, it comes to my output. So whenever my y is 0, irrespective of 1 and 0, the output comes here. Correct? So this is what is my reduced state table. Okay, so these are my possible combinations. Now dear students, now keeping this in mind, okay, now you can see this reduced table. So from this reduced table, I'm going to draw the state diagram. You can have a look of the state diagram. So here we know that, see, I have written clearly for you all what is the position of A and what is its output. So let me write this like this. So A is 0, 0 with an output 0, correct? So B, let me write B for you all here. So B is, see, you can see B is 0, 0 with an output 1, correct? This is my B. And C is what? C is 0, 1 with an output 0. This is my C. So let me write D over here. So D is what? D is 1, 0 with an output 0. You can see in the table also. D is 1, 0 with an output 0. So what is my E? My E is 1, 0 with an output 1. What is my F? F is 1, 1 with an output 1. Okay, I can draw it like, you know, in a random sequence or however you wish. Okay, now see here, seeing your reduced state table, how do I connect this state variables? Okay, now 0, 0 goes to 0, so it goes back to the same place. Okay, now 0, 1, 0, 1 is what? 0, 1 is your C. Okay, so A comes to, this is A, right? This input is A, so A comes to C. You can see here, A, 0, 0 is A, so A comes to C. So A comes to C. I'll represent this with the green pen. So A comes to C. Okay, so its output is 0 over here. Next you can see that A is coming to the next condition 1, 0. What is 1, 0? 1, 0 is, so this is A, B, C, this is D. Okay, A is coming to D. So I'll write this as A is coming to D. Okay, the output is 0. Coming to the next block, you can see B here. B's condition is 0, 0 with an output 1. So B is coming to the same state. So I'll write it for the same state here. Next, B is coming to 0, 1. 0, 1 input is where? 0, 1 is to C. Okay, so B is coming to C. Okay, next is B is coming to 1, 0. B is coming to 1, 0 is, here it is E. So B is coming to E. Okay, with the output 1. Okay, the next condition is 0, 1. 0, 1 is C. So it's coming to the same state. So I'll mark it like this. So C coming to the next state, 0, 1 to 0, 0. 0, 0 is nothing but your A. So it is going back to A. Okay, from C to A. Next, C is coming to 1, 1. C is coming to 1, 1 is to your F with an output 1. Okay, now coming back to D. D is going to the same state. So I'll represent like this. Next, D is going to 0, 0. So D is going to 0, 0 is A with an output 0. Now D is going to 1, 1 with an output 1. That means D is going to F. Okay, with an output 1. So E. So E coming to E. So E 1, 0 goes to the same state, of course. Then E is going to A. So E is going to A. I can represent like this. Okay. Next is E is going to 1, 1. E is going to 1, 1. That is F. Okay. And the next condition, the last condition is FF. So FF going to the same state. And F is going to 0, 1. So F is going to 0, 1 is here to C. Okay. Then 1, 0. F is going to 1, 0. So F is going to 1, 0 is nothing but your D. So F is going to D. Okay. F is going to D. Okay, yes, you have understood the sequence. Okay. So students, we saw that from the reduced state table, how we came to the state diagram, right? So we analyzed each and every possible inputs and we have come, or we have ended up in the state diagram. Okay, now the next step is, okay, step 3 is to, this will be, sorry, this is a step 3. Drawing the state diagram is a step 3. Now let's see the step 4. Okay, so let's see the step 4. So considering the same, this is a step 4, to draw the primitive flow table. Okay, so this primitive flow table again can be framed using our previous reduced state table. So how do we do this is, so let us write all the states which we have got. Okay, so we have 6 states: A, B, C, D, E, F. So it is A, B, C, D, E, F. So we have our inputs. So our inputs are 0, 0, 0, 1, 1, 1 and 1, 0. Okay, so these are our inputs. Okay, now see this, see our reduced state table. For the input 0, 0, okay, it is going to the same state, right? So I'll write here, it's going to the same state. Okay, and my output is 0. So my output is 0. Now A, 0, 0 is A, right? A is going to 0, 1. What was 0, 1? We know that 0, 1 was C. You can cross check in the previous step. So A was 0, 1. So it is going to C, and my corresponding output is 0. Now again A is going to 1, 0. So 1, 0 is D, right? 1, 0 is D, and its output is 0. I'll write that for you all if you want. A is 0, 0. B is 0, 0, C is 0, 1, and D is 1, 0, and E is 1, 0, okay, and F is 1, 1, right? This was the state which we have mentioned in the state diagram from the previous inputs. Okay, now here we know that the input is 0, 0 for A. So the race condition is what? Race condition is the 2-bit change, right? If the 2-bit has to change here, then 1, 1 is the race condition for A. So here 1, 1 is the race condition. So we don't specify any inputs. So you will just represent it with a dash. Now coming to B. So B, when it is 0, 0, it goes to B itself, right? So B, when the input is 0, 0, it goes to B itself with the corresponding output being 1, right? So B goes to 0, 0 goes to 0, 1, 0. So 0, 1, 0 is 0, 1, 0 is your C. So I'll write it as C over here, and its corresponding output is 0. Now B goes to 1, 0. So B goes to 1, 0 is what? B goes to 1, 0 is your B goes to 1, 0. So here it is E, right? With the output is 1. Okay, because for E10 with output 1 specifies E, that is why I have written E over here, and 0, 0, the race condition again is 1, 1, correct? So here it is dash and dash. Okay, now coming to C. So 0, 1, 0, it goes to the same C. So here it is C, and since it's the C, I'm encircling it. So C goes to A, 0, 0. So C goes to A, 0, 0 when the output is 0, and C goes to 1, 1 when the output is 1. So it is 1, 1 is F, okay, when the output is 1. So what is the race condition of 0, 1? So 0, 1 race condition is 1, 0. So for 1, 0, it will be a dash and dash, okay. Similarly for D, for the condition for D, so 1, 0 is D, right? 1, 0 goes to 0, 0 A. So when its corresponding input is 0, then the race condition 0, 1 will be the race condition, and next is D goes to 1, 1. So it is F at the input 1, sorry, the output being 1, and the last is D, 1, 0 is D. So the same state it goes when the output is 0. Now coming to E, E is 1, 0 with the output 1, so it goes to same state 1, 0, same state with the output 1. Okay, so the next is E goes to A when the output is 1, and 0 0, A is 0 0, and E goes to 1 1. So E goes to 1 1 is F here, and the output 1, and this will be its race condition. The race condition of E is what? If it is E is, as we know, that 1 0, so the race condition will be 0 1, and for the D, if it is 1 0, the race condition will be 0 1, right? So this will all be given as dash. For F, so 0 0, for F is 1 1, so 0 0 will be the race condition, so this goes as dash dash. And the next is F will come to 0 1, that is C, so it is C, okay, with an output 0. And F coming to 1 0, that is F coming to 1 0, that is E, with an output 1, and F goes to the same state F with output 1. Okay, so students, I understand that your primitive float table is easy, so this is exactly filled by using your reduced table. Okay, so the next step is you have to draw an implicit, okay, implicit table. Students, listen carefully. How to draw the implicit table is, since we have 6 states, your implicit table should be drawn for 5 by 5 states. Okay, so how do I draw this? Is with 5 rows and 5 columns. Okay, so you can see this. So 5 rows and 5 columns. 1 2 3, so here you will get one more. Okay, so here I should start from B, B, C, D, E, F, and here it is A, B, C, D, and E. Okay, now just compare A with B, A with B. Now you can compare A with B. See, when you're comparing with A and B, all the positions has to be same. Now A and B, you can see the outputs are all changing. Even if one variable changes, there is no match. So A with B is not matched. Okay, so coming to the next case, A with C. Okay, compare A with C. If you compare A and C, you can see you have the same variables, A comma 0, C comma 0 with C comma 0, and here you have a dash dash. This dash is considered as don't case, which you can fill with any term. Okay, so here we have F1, so this can be filled with F1 over here, and you can consider D0 here. Again you have a dash dash here, which can be filled with your don't case, so this can be filled with D and 0. So your A and C are alike, so I will go ahead and put a tick over here. Okay, now compare the next A with D, A with D. Okay, here we have compared A with C. Now you can compare A with D. Compare A with D. You can compare A and D here. You can see that A comma 0, A comma 0, C comma 0. You have a don't case here, which can be filled with C comma 0 here. You have F comma 1 here and dash, which can be filled with F and 1. And you have D0, D0. So A and D is alike, and you can put a tick over here. Okay, now A and E. A and E you can compare. A and E, see, you can see the output is not matching, so I'll just put an X. Okay, next is F. A and F. You can compare A and F here. Okay, you can see here A and F, again it is not matching because you can see one of the output is not matching. Even if one term doesn't match, you can just cross it. Okay, next is B with C. B with C, you can see B and C, you can see it is not matching over here because you have A and B here, 1 and 0, it's not matching here. D with B with D, so B with D, again it's not matching, you can cross verify. And next is B with E, so take B and E. Okay, so you have B and E, so B and E is here. So don't case, you have F term and you have a F term. Okay, so this matches because everything is matching here. And next B with F. If you take B with F, you have don't case, which will be matching, and here you have the same terms, C comma 0, Fn and E comma, so this matches, right? And for the next case, D and C, for D and C, if you see, it is exactly matching. And for C and E, C and E, okay, it is, the outputs are changed, so it's not matching. For C and F, it is same, it is matching over here. For D and E, it's not matching. For D and F, if you see, it is not matching. For E and F, you have, it is matching. Okay, so E and F you're matching. Okay, so this is how you fill the implicit table. Dear students, now using this implicit table, the next step is, okay, next step is to draw the merger graph. Just see carefully, how do I draw the merger graph? Now you can see that, okay, whichever we have ticked in, okay, we have ticked AC, okay, we have ticked AC, right? So I just draw the circle consisting of my 6 states. Okay, so let me name this as A, this as B, this is C, this is D, this is E, and this is F. Okay, now A and C is having a match, right? So I'll just connect A and C. So whichever I have picked in, I have to connect. Okay, next is AD. So AD, I'll match. Okay, next is, you can see here, CD. Okay, so CD I'll connect. Next tick against B and E. So B and E I'll match. I'll draw a line. Next is B and F. Okay, towards B and F I'll match. Okay, so next is E and F. E and F I'll match, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and CF, there is a CF, C and F, there's a tick, so I'll have to draw the line here. Okay, so these are my connecting lines for all the tick marks. Okay, this is how you draw the merger graph. Now dear students, see carefully. For, I can see that 2 triangles over here, right? So 2 triangles is, one is BEF, another triangle is ACD, right? I have 2 triangles, ACD is one triangle, and my other triangle is BEF. Okay, so ACD forms the closed path, so I can consider C and D to be equal to A. Similarly, BEF forms the closed path, so I can consider, okay, BEF forms the closed path, so I can consider E and F to be equal to B. Okay, so these 2 triangles connects my important points. Okay, now if you consider the line EC, this EC does not have or does not play a major role. Okay, because this is not going to be a part of my triangle. Okay, and this is not going to contribute for any closed path, so I can eliminate this particular line FC. Okay, so by eliminating FC, I get a reduced state. This is one of the important or the major advantage of a merger graph. This is very important, and that is why the merger graph is being used. Okay, then let us come to the primitive flow table. Dear students, now the next step is primitive flow table. Okay, so how do I draw or how do I frame the primitive flow table? That is nothing but the reduced primitive flow table, because already primitive flow table we have C. Okay, now this is really easy, just you can have a look. Okay, so here we have 0, 0 are inputs, 0, 1, 1, 0, sorry, it's 1, 1 and 1, 0. Here from the merger graph, I'll write DC is equal to A, and from merger graph EF is equal to B. This we have got from the 2 triangles, right? So we can see the primitive table. Okay, here only A and B should be used. Okay, now see here. So if I have to say, okay, if we can take the primitive table, so students, as I told you all, the reduced flow table can be obtained from the primitive flow table. In the primitive flow table, if you see, our A is what? 0 0 with an output 0. So I'll write this as A comma 0. Okay, and 0 1 is what? 0 1 is C, so it is C with an output 0. Okay, so 1 1 is what? F with an output 1, so I'll write this, and 1 0 is what? 1 0 is D with an output 0. Okay, so let's fill this row now. Now B, so 0 0 is B with an output 1 because it represents B here. 0 1 is nothing but C with an output 0. Now 1 1 is F with an output 1, and 1 0 is E with an output 1 because E belongs to here. Okay, now this is how you will have to frame the reduced primitive flow table, and this you fill by using your primitive flow table, the initial inputs. Okay, now after this what we have to do is, okay, as we know that DC is equal to A, I can replace this C. DC is equal to A from the merger graph, and EF is equal to B from the merger graph, right? So wherever you have C, I can just name it as A, and F belongs to B, so I can write it as B here. D belongs to A, so I can write here A, and C belongs to A, I can write A here. F belongs to B triangle, so I can write B here. E belongs to B triangle, so I can write B here. So everything is replaced with only two inputs, that's your A and B. This is what is your reduced primitive flow table. This you can write it neatly. Okay, and the next step is to draw the K-map for the next state and the output. Okay, so here the next state is, okay, the next state and the output, we'll have to draw the K-map. Now we have represented everything in terms of A and B. So there is only two inputs, A and B. So value of A I can consider as 0, and value of B I'm considering as 1 because there is only two inputs. Now let me replace this. Okay, so we have considered only A and B, so let me replace this. So now you have A is 0 because we have considered A as 0, and this output I'm going to make that as 0 itself. Now here again it is A, so it is 0 and 0. Here it is B, it is 1 comma 1. Here it is A, 0 comma 0. Here it is 1 comma 1. Here it is A, so 0 comma 0, 1 comma 1, and 1 comma 1. Right? So here it is 0 and 1 because here it is A and B, so I'll replace this. So here this I am writing it as F, and these as my XY inputs to draw the K-map. So my inputs I'll give as 0 0 0 1 1 1 and 1 0. Okay, so now we'll have to draw the K-map for two possible cases. Okay, so one is for the next state, which I can represent as F plus, and the last case is for the output. Let me represent the output as, okay, say Z or something. Okay, now the first input, or something before the comma, is what is your next state or the input, and something after the comma is your output variable. So this is your next state input or next state, and this is your output. So let me write the K-map and group it for you all. So this is 0 0 0 1 1 1 1 0. So here you have 0 0. If I am segregating only the inputs, so the first term I have something like this. Okay, so if I have to group this, now this is F and this is XY. So my grouping will be, so this is my K-map grouping. So I'll get the expression as f plus is equal to xy plus f y bar, right? So similarly, if I have to group for the output, so the same thing. So in this specific problem, you will get same terms, okay? So here only the output I'm taking, so 0, 0, 1, 0, 1, 0, 1, 1. So my grouping will be something like this, okay? So I'll get the sum terms for output, which is xy plus y f y bar, okay? So as I told you, so I've grouped all my inputs in one K-map and all my outputs in one K-map. So I got my next state as well as I've got my outputs, okay? These are my two expressions, K-map expressions. And the last step of the asynchronous sequential circuit design is your logic diagram. And since this logic diagram is same for both the cases, okay, so let me draw that. So you have f plus is equal to xy plus fy bar, and the output is also the same, right? So I'll take my two inputs as xy, connecting with an AND gate, and I'll take my other input f and y bar. I can either take it directly or you can connect a NOT gate, it's up to you, and both is finally connected to an OR gate. So this is your output, your next state and your output, okay? So this is your logic diagram, and this logic diagram finally completes your asynchronous sequential circuit design. So dear students, I hope you have understood the steps. So for any doubts and clarifications, you can revert back to me. Thank you.